All right, this talk will be given by Yaofeng Xie from Rice.
Yes, it's a serious
About room temperature, spin, nematic, and anomalous oil effect.
Good afternoon, everyone. My name is Yaofeng, and I am from Professor Pendendi's group at Rice University. So today I will talk about our recent work on the discovery of room temperature spin nematic phase in a tetragonal antiferromagnet ytterbium manganese business 2 compound, and how it's connected to the anomalous Hall effect in the system. Here is an outline of this talk. First, I will briefly introduce about anomalous Hall effect and its possible origin, and then discuss a little bit about the spin orders, not only the conventional ferromagnet and antiferromagnet, but also the more exotic composite spin orders such as spin nematic and the scalar spin chirality. Then this would lead us to the puzzle in the ytterbium compound, because the system is reported to be a collinear antiferromagnet. So by symmetry, it should forbid a large anomalous Hall effect. But the experimentally, the transport and pulse measurements actually show a giant anomalous Hall effect, and also the wild points in the band structure. So this motivated us to use polarized neutron scattering to try to reconcile these contradictory observations to resolve the spin canting and also the spin anisotropy. And eventually we established a new mechanism for the anomalous Hall effect in the system. So what is anomalous Hall effect? So let's first look at this normal Hall effect. So in a material, when we apply an electron current along the x-axis and a magnetic field along the z-axis, it will generate a transverse voltage. This is a normal Hall effect. However, in the ferromagnets, there is an extra contribution at the lower field, which is proportional to the magnetization of the ferromagnets. So this is called anomalous Hall effect. And traditionally, people associated this anomalous Hall effect with the broken tight reversal symmetry in the ferromagnets. And in recent years, people also realized that anomalous Hall effect can also be observed in antiferromagnets, provided that the spin structure is non-collinear, or if there is some small canting, small spin canting. So now we see that the anomalous Hall effect is actually a fingerprint of the broken symmetry in the system. So what's the possible origins of the anomalous Hall effect? In the momentum space, the well points can act as monopoles of the barrier curvature. And the barrier curvature is basically a fictitious magnetic field in the momentum space that can bend the motions of the electrons to produce this Hall effect. And when the inversion symmetry or the time reversal symmetry is broken, the well points can appear in the in a material. And in the real space, these three spins can form a triangle of non-coplanar spin texture, and this is called a scalar spin chirality. And this scalar spin chirality can also act as a fictitious field in the real space, which can also generate the anomalous Hall effect. And a famous example is the skirmion. And most recently, the automagnets are also proposed to host this anomalous Hall effect because of the momentum-dependent band splitting. Yeah, so, and to understand what kind of spin texture can generate the anomalous Hall effect, let's talk about the spin orders. In a conventional case, we can use a single spin order parameter to describe the system. For example, in the ferromagnets, all the spins aligned in the same direction, while in the antiferromagnets, the spins alternate. So here, both cases break the spin rotational symmetry. And in the ferromagnetic case, it can generate an anomalous Hall effect. And the nature actually allows more exotic composite spin orders. One example is the spin nematic here. So you can think of spin nematic as liquid crystals of spins. The average momentum cancels out to be zero, but the true spin correlation, like this, how the pair of spins fluctuate together, they are actually anisotropic. But as shown in this schematic, this pair of spins, they prefer to fluctuate in the vertical direction rather than the horizontal direction. So this case In this way, they break the spin rotational symmetry in the spin space, but there is no net magnetization. And another example is the previously mentioned scalar spin chirality, which is 3 spins from these non-coplanar triangles. And this scalar spin chirality also breaks the time reversal symmetry, and it can generate the anomalous Hall effect. So now we say that both one spin and 3 spin correlation can induce the anomalous Hall effect. It would be very interesting to study how the spin nematic, which is a 2 spin correlation, can be related to the anomalous Hall effect. So now let's look at a specific puzzle in the equilibrium compound. It is reported to be a C-type collinear antiferromagnet with a near temperature about 290 Kelvin. And its space group does not break the inversion symmetry. So it should not host a large anomalous Hall effect or the well points, but the experiments tell a different story. As you can see here, the anomalous Hall effect actually persists to up to 250 Kelvin in the transporter study, and APAS measurements observed these well points in the band structure. So to explain these well points, they actually proposed the manganese spins, both the spin up and the spin down spins should candidate towards the same direction with in the AB plane. So that canting would produce a ferromagnetic component within the AB plane, and this ferromagnetic component can break the time reversal symmetry to induce these well points. And their calculation actually proposed this canting angle should be about 10 degrees. So now the question is whether there is actually spin canting in a box sample of the equilibrium compound. So to address this issue, several neutron diffraction studies have been carried out. They actually all consistently find that the spin structure is strictly collinear. There is no spin canting in the AB plane. So one of the studies shown here, they actually measured the temperature dependence of the 001 factor, which is probing the AB plane moment. So if there is actually like an APAS work proposed, if there is 10 degrees spin canting, then the intensity of the 001 bright peak should increase according to this green line. So essentially, their analysis shows there is no spin canting, and if there is a spin canting, the canting angle should be less than 3 degrees. So this would leave us with an open question: what is the driving force for this anomalous Hall effect in this system? So our objective is to use polarized neutron scattering, which has some unique advantage compared to the unpolarized one, and to conclusively determine the spin structure and try to identify the mechanism of the anomalous Hall effect. So the basic idea of polarized neutron scattering is that by controlling the polarization of the incident and the scattered neutrons, we can actually measure the spin flip and non-spin flip scattering, which correspond to the magnetic and non-magnetic signals. And we can further polarize the neutron along this coordinate, the x, y, z direction. And this coordinate is defined with respect to the scattering factor Q. And by measuring these 3 different polarization cross sections, we can actually resolve the magnetic response along this crystalline ABC axis. So in the elastic case, when we do the diffraction, we can measure the magnetic moments along the ABC axis. And in the inelastic case, then we are measuring the fluctuating moment along the ABC axis. So we define this magnetic response as NA and B and C. So here I'm showing the polarized neutron diffraction results. So again, if we want to measure the moments within the AB plane, we choose this 001 factor because neutron is only sensitive to magnetic moments that are perpendicular to the scattering factor Q. So this is showing the raw data of the 3 polarizations at this 001 factor. And without going into the details, I'm telling you that this intensity difference between the sigma x and the sigma y is corresponding to the magnetic moments that along the b-axis. And this intensity difference between sigma x and sigma z is corresponding to the magnetic moments along the a-axis. So both cases shows there is no observable intensity. So it basically means there is no AB plane moments, which is consistent with the unpolarized studies. And then when we're using the 100 factor, we can probe the dominant z-axis moment, which is shown in the middle panel here. So the sigma x minus the sigma y is corresponding to the z-axis moment. And we can further do a detailed temperature dependence to extract this autoparameter, which gives us the new temperature about 290 Kelvin. So all these are consistent with the unpolarized neutron scattering studies. And the unique advantage of our polarized technique is that we can compare the integrated intensity of this MB with the integrated intensity of this NC. So in this way, we can place an up bound of the Canning angle, which is less than 0.3 degrees, which is much smaller than the 10 degrees proposed by the APAS work. So, actually during our investigation, we also noticed that there is a sister compound, calcium manganese bismuth 2. It shares the identical nuclear and magnetic structure as the ytterbium one. And interestingly, there has been no reports of anomalous Hall effect in the calcium compound. So it is very interesting because they share the same magnetic structure, but they behave differently in terms of the transport. So we also tried to completely understand this system. We also did the polarized diffraction in the calcium sample. And the result is the same as the ytterbium one. They are strictly collinear C-type antiferromagnet. And we also used the single crystal neutron refinement to confirm the nuclear space group. There is the inversion symmetry is preserved, and we confirmed the magnetic space group. It excludes any spin canting towards the AB plane, and they are not automagnets. So now the question is that since the static spin structure cannot explain the anomalous Hall effect, we want to study the spin dynamics. So this is showing the previous inelastic neutron scattering studies. They map out the spin waves along the high symmetry directions. And the bottom panel is showing the temperature dependence of the spin anisotropy gap. And the spin wave is actually quite conventional. They can be well described by a Heisenberg J1, J2, and JC model. So in a sense, these conventional magnons cannot explain the anomalous Hall either. So it motivated us to go further to use the polarized inelastic neutron scattering to resolve any potential spin anisotropy. So here I'm showing our polarized inelastic neutron scattering results. The top two panels are showing the three polarization cross sections at 100 and 102 factors. They are equivalent antiferromagnetic wave factors. So as I mentioned, when we probe at this is 100 and 102 factors. So when we probe at 100 factor, we are probing the magnetic response within the KOL plane. And if we choose a different 102 factor, we're actually probing this magnetic response within this plane. So by combining these two measurements, we can deduce these spin fluctuations along the A, B, and the Z axis, which is shown in the bottom panel. And at least 230 Kelvin, we can say that the spin fluctuations along A and B axis are equivalent, but the fluctuations along the C axis are almost zero. So this is consistent with a localized model because the static moment is along the C axis. So the fluctuating moment can only be along the perpendicular direction, which is A or B axis. And these two should be equivalent as well. But when the temperature is 300 Kelvin, which is slightly above the new temperature, we would expect the system to be in the paramagnetic state. That means the spin fluctuations along the A, B, and C axis should be isotropic. But actually, we observed the strong anisotropy between the NA and NB here. So this data, sorry, at this low energy range, the spin fluctuations along the A-axis are much stronger than the fluctuations along the B-axis. And on further warming up to 400 and 450 Kelvin, the spin fluctuations become isotropic again, without even though there is some sort of spin gap-like feature reopening. So this spin anisotropy here is quite surprising. We tried to we want to understand it better, so we did a very detailed temperature dependence. As you can see in the panel A here, this is showing the temperature dependence of 3 spin fluctuations. At 450 Kelvin, they are isotropic, and as we approach Tn, the fluctuations increases, and they peak around Tn, and they got suppressed below Tn because of the spin anisotropy gap. The most interesting thing is the difference between NA and NB, which is the AB plane spin anisotropy. As you can see, they almost follow the same temperature dependence. They are isotropic at high temperature and peak around Tn, and then got suppressed below. For comparison, we also show the temperature dependence of these spin fluctuations at high energy, which is 9 millielectron-volt. So the fluctuations along A and B axis are almost isotropic at this high energy range. So this spin anisotropy at low energy is quite surprising, but it is consistent with the definition of a spin nematic, which breaks the spin rotational symmetry in the spin space without the long range magnetic order. So basically, we discovered an hidden phase of this system. And another question is that whether this spin nematic phase can be related to the anomalous Hall effect. To address this, we first extend the anomalous Hall effect measurements to all the way up to 400 Kelvin. You can see for ytterbium compound, the anomalous Hall effects onset almost at the same temperature as the spin nematic, and they all peak around Tn, and then gradually got suppressed below Tn. In contrast, the anomalous Hall effect in the calcium compound is much weaker, about 1 magnitude weaker. And it is very exciting that both the anomalous Hall effect and the spin nematic in the ytterbium compound share the same temperature dependence. But we should note that the spin nematic itself does not break the time reversal symmetry. So by itself, it cannot induce the anomalous Hall effect. There should be some additional magnetic contribution that couples to this spin nematic to induce this anomalous Hall effect. So it led us to think about the role of the ytterbium ions. We performed the X-ray photoelectron measurements, and the ytterbium ions actually has a mixed valence. Both 2+ and 3+ are present. And the 3+ ions can carry a magnetic moment. And this magnetic moment, this ytterbium magnetic moment can couple to the two magnetic spins of the spin nematic to form this triangle of non-coplanar spin chirality, a scalar spin chirality, so which could potentially induce this anomalous Hall effect. And this also naturally explains why the anomalous Hall effect in the calcium compound is much weaker, because the calcium ions cannot be magnetic, so there is no such triangles of scalar spin chirality. So to bring all the experimental observations together, our theoretical collaborator developed this phenomenological model. The relevant order parameters are the new order, the nematic order, and the scalar spin chirality. So in this model, the nematic order emerges due to the spontaneous symmetry breaking in the spin space, and the new order emerges due to the spontaneous symmetry breaking in the real space. And the Liax by symmetry in their model, there is a coupling term between the spin nematic and the scalar spin chirality via the external applied magnetic field. And this coupling term is very important in terms of induced anomalous Hall effect, because when we do the anomalous Hall measurement, we actually apply an in-plane magnetic field. And when we apply this magnetic field, the ytterbium, the moments of the ytterbium ions actually become field polarized. In this field polarized state, the ytterbium ions can actually act as a spin catalyst to greatly couple to this spin nematic of the two magnetic spins. Then this coupling can greatly enhance this scalar spin chirality to greatly enhance the anomalous Hall effect. And in the calcium one, there is no such additional spins, so the anomalous Hall in the calcium compound is much weaker. So to summarize, so our polarized diffraction studies actually confirms that both ytterbium and calcium compound are strictly collinear antiferromagnets. There is no evidence of spin canting, and they are not automagnets. And our polarized inelastic neutron scheduling study reveals a spin nematic phase, and eventually we identified a new mechanism of this anomalous Hall effect. And before wrapping up, I would acknowledge all the collaborators who made this work possible. Yeah, thank you for your attention.
So I'm confused towards the end of your talk. So at the beginning you said there's no canting, but it seems near the end you're saying when you apply an infinite magnetic field, there's canting of the ytterbium ions that lead to the anomalous Hall effect. So canting or no canting?
For the manganese spins, the static spin structure do not have canting.
Yeah, but it seems you're ascribe the anomalous Hall effect to the canting of the ytterbium. So like can't just the magnetic canted ytterbium ions lead to the AHE alone? You really need a higher order effect?
Yes, because when you apply magnetic field, before you apply magnetic field, the ytterbium ions are actually in the paramagnetic state, so their spins are randomly distributed. When you apply a magnetic field, the ytterbium ions become field polarized. Only the field polarized state can couple to the spin nematic of the two magnetic spins.
Yeah, so my point is you need the spin nematic state.
Yes, yes. Otherwise, you cannot form this three spins scalar spin chirality.
The field is small enough. You're not going to can the manganese moment. I mean, the ytterbium is actually a separate polar market. So the ytterbium moment can be polarized at any temperature, any field. Okay, so he's basically claiming is that the ytterbium moment is coupled with the spin, scalar chirality, and with the spin nematic phase. That's dynamic, because everything he sees is actually above Tn. There's no manganese moment either. There's no order moment either, right? Because he's seen the spin anomalous Hall above Tn. Above Tn, then when there's actually no order of any type, canting concept in the past.
It only happens when there's a nematic phase.
Yeah, because he's seen anomalous Hall at a temperature above Tn. I mean, there's no such a concept as canting. Yeah.
Other question?
I have a little bit many questions. Because some of this non-two compound is known to have become a little bit of one way, like some calcium, manganese, and you rule out any possibility of a little bit of visit in the tissue function.
I guess we try many different methods to both polarized and unpolarized and single crystal neutron refinements. Within our detection limits, we don't see any orthorhombic signatures.
They're actually are given peaks to appear. I mean, there's no evidence of.
Yeah.
Yeah.
So with this mechanism, is it possible to predict some other compound with larger antiparticles and larger, more pronounced?
Yeah, I think it's possible if you know induce a stronger spin orbital coupling in a system, in a similar system, because the equipment actually is the reason why there is a strong spin orbital coupling. Yeah.
Thank you.
Yeah.